Testing, testing. Okay, now it's fine. Okay, so just to recap what we have done last Friday, on Friday, we first I told you how to use scripts in Excel. We had an exercise. I was kind of doing it in class. I showed you. Then I told you that we came to this concept of production potential, okay, which is simply the maximum field rate that you can produce for a particular GP, okay, cumulative production. In our case, we did simply running simulations, simply running for each time step, setting the choke equal to 0, and then we recorded like this profile. That is, if the field was produced in mode B. I told you that might not be possible for some mechanical constraints, okay, because you want to reduce the rate per well, so you might have to increase the number of wells. But you know, theoretically or using the models, that's what it's giving, okay, the maximum rate that it can produce at any given time. Then for each time, we associated that value with the cumulative production, and we ended up having a curve like that, which is kind of resembles like a straight line. And I told you that we can use this curve for two things. One of them was to find out the plateau duration, okay, because I told you we come with our desired plateau duration, I think it's here, we intersect with that curve, we read the value of GP, and then from there we calculate the time, okay, we divide the GP by the Q of the plateau, and that tells me the number of days that you will be producing, okay, because at this GP, when you reach that GP, or that will be equivalent to reach that particular reservoir pressure, then you won't be able to sustain the plateau any longer, and you will enter in decline, okay, when you go above this production. The good thing is that if I have produced up to that time with a constant rate, simply the time is just dividing both, okay, the GP divided by that rate. However, 4 times early, or for GPs from 0 to that number, okay, I could produce more, but I'm deciding to produce less. Okay. Then we had one example where I told you if it's a straight line, like in this case, we can do an analytical derivation of the rate. If the time is less than the time of the plateau, then simply the field rate will be the desired plateau rate. But if it's greater, then I will be operating at potential. That means if it's greater, I will be operating on that line. Okay, and then I substitute the equation of the potential, then I clear this variable here, and that gives me a kind of an exponential decline. Okay, and that's also like a justification. Exponential type declines are used for many things, decline curve analysis, to forecast the production of wells, especially onshore, small fields, that they use expression like that. Okay, and it has some, you see, we were using in our example all kind of thorough equations. We were not using any approximation. Okay, however, this potential ended up to be like fairly straight. Okay, and then if we do that approximation, we obtain a kind of an exponential decline. Okay, which is like justifying why we can use an exponential model for some things. Okay, if the production potential is a straight line, then we can use a decline, an exponential decline. Okay, and I told you maybe for the exercise will be better to use that expression if you can profit somehow from that expression, and don't do the calculations every time. Okay, ways to prolong the plateau and how to decide on plateau rate, on number of wells. That's something you'll have to do in the exercise. Yeah, also, so I want to make a few comments for today. I think we better, I think that comment, let me just take that away. Okay. So one thing is, let's say, some comments on production potential. Okay. So for example, if you change the number of wells, it will change. Okay. Changing number of wells okay. So for example, if we're saying that our QPP, production potential, versus GP, we're saying we have a base case like that. What will happen if I increase the number of wells? So let's say that's with number of wells 1. Okay. What happens when I increase the number of wells? Should it be the same curve? Should I obtain more, or should I obtain less? More. Okay. So if you add one, for example, some more wells, then you will be able to produce more at the same reservoir pressure. Okay, and that trend actually continues throughout time. So n wells 2, and here n wells 2 is greater than n wells 1. So that's why I told you have to be careful if something changes in the system, like number of wells, for example, then you cannot use the same equation. Okay, you cannot use the same curve. And also the same thing, if you have less number of wells, then it will be like that. Okay, number of wells 3. Okay. Another thing, for
will all the curve will follow same slope? It may be different, right?
yeah, it will be different. Okay, usually they have, even though you don't know why, you have to make the calculation. They have some, so here they are spread, but here the separation is less. They are kind of converging to the same point. But you have to do that test. That's kind of what you can say is bigger or smaller, but to know exactly how it will change with GP, you have to run a model. Okay, to calculate this curve, you have to run what we have done, like we did last time. You know, we ran a kind of an Excel model. Okay, for example, maybe another question: what happens if I increase tubing size with GP and QPP? Okay, the tubing. Okay, let's say I have the base case, which will be the tubing 1. Usually when I increase the tubing, I'm able to produce more, right, for the same reservoir pressure. So you have a similar effect as the number of wells. Not as pronounced, okay, but you have an increase in this potential. Okay, let's say not that pronounced, maybe a little bit more. DT2, and if you decrease it, then you have slightly less production, DT3. Okay, and here diameter 3 is less than diameter 1 and is less than diameter 2. Okay, so every change we make, that was my point, every change we make in our production system will give me another potential line. Okay, so you can use it, you can see, okay, I have a unique curve, I use it for calculating plateau end, I use it to calculate decline production, but you have to be careful if anything change in the system. Okay, if anything change in the system, you have to see how that affects your maximum rate, and if that affects it, then you have to run again a simulation to calculate this potential, which then you lose the purpose a bit of using the potential, because you use the potential simply to avoid using the full complex model. Okay. What else? So changing also, what happens if you changing G, okay, also modifies the potential. Okay, remember what was G? Was initial gas in place. So if I have a base case, QPP versus GP, okay, that will be for G1. Okay, what happens if I have a bigger reservoir? Okay, so first let's go for the simple part. How will be the initial point? Will it be any different if it's bigger reservoir?
It depends on the field rate. If we want to continue with the same field rate or we want to increase it.
Yeah, but this is the maximum rate that the field can produce. It's exactly the same system.
Yeah, then it will be same.
Okay, at origin, okay, at zero, it will be the same because the reservoir pressure is the same for both. Okay, but when you start to decline, when you drain, for example, this amount, you will reach a higher reservoir pressure than the smaller reservoir. Okay, you won't decline pressure so quickly. So that's why if you increase G, it's something like that. Okay, G2. Here G2 is greater than G1. Okay? Because simply you have at this particular point when you have produced this amount, simply reservoir pressure hasn't dropped that much because you still have a lot of volume in the reservoir. Okay? While if you have a smaller reservoir, then the opposite will happen. Okay, something like that. Okay, G3, and here G3, it's actually smaller than G1. Okay, so if I have certain plateau rate, okay, Q plateau, which one gives me which curve maximum plateau duration?
G1, G2.
Okay, G2, because simply it will arrive, the GP star at which you end up the plateau will be higher. Okay, and you are dividing always by the same. So you have GP star 2, GP star 1, here you have GP star 3. So simply the T plateau will be GP star 3 divided by Q plateau, or it will be GP star 2 divided by Q plateau, or it will be GP star 1 divided by Q plateau. Okay, and in all these cases I want to produce the same rate, right? The only thing is the intersection with the curve. In this case the biggest number is GP2. Okay, it's when I intersect with the big reservoir. And if you want to see like applied to field development, during the development phase of a field, there is a big uncertainty in G. Okay, so it has some effect on the duration of the plateau first and also on the decline. Okay, one of the things is something we are deciding upon. We are deciding on that number, but the other thing might be something like an uncertainty. Okay, the uncertainty might cause the curve to be more stretched to the right or smaller to the left. Okay, and both have an effect on my production profile.
I have a
Yes.
So if we have a high G value, so shouldn't it be the case that we also have high reservoir pressure compared to low G reservoir?
Yeah, the reservoir pressure is something that you can measure, of course, not from seismic, but from exploration wells.
Yeah.
Okay, so it's something usually you are very sure about the reservoir of the container.
I'm asking in general, if we have high G value, then reservoir pressure should be more compared to low G reservoir, right?
Yeah, it's not so easy to generalize. That's usually the case, but it's not always the case. So I will say simply, reservoir pressure is something you're very sure. You measure by exploration drilling, and the G is very uncertain. Okay. It can be that you have simply a small pocket, but it's at high pressure for some reason. Okay,
Yeah.
but so then it's not so you cannot correlate both. So okay, yeah. So then I just want, before we forget about production potential. Okay, you will have, I think, one part of the exercise will be on that. Okay, and I told you can use it, but be careful what affects this production potential. Okay, the G is affecting it, the number of wells, if you change the tubing diameter, if you change anything in your system that affects your maximum flow, that's going to affect your potential. Okay, but so how can we use QPP, the curve of QPP versus QP? Okay, QP here I'm referring to either N or G, okay, because that's a more general case. I can have oil or water, to estimate Q of the field. Okay, because we have that, we can know how to estimate the end of the plateau, but we want to estimate the Q of the field, let's say post-plateau. Okay, and the first answer is what we have done already before, which is analytical derivation. If the QPP versus QP is, how do you say, if you can integrate it, right? Because you remember we substitute in the expression of, okay, we did this last class. Okay, we substitute in the expression of the potential, cumulative production, and then from there we had to solve this equation. Okay, so if it's easy to integrate, then I can use analytical derivation if is easy to integrate. Okay, and if not, you can do time-wise calculation. Okay, so it will be something like that. For each time with for each time with how much you have produced, right, for that particular time, read or interpolate in the curve okay, the QPP of that at that QPT. Okay, so that means, let's say you're at time 0, you have a curve which is like that, QPP. Okay. And at time 0, let's say you have no production, simply you read the value on the curve and you have your maximum. Okay. Let me just change here. I read in the curve, or you can have a table. Okay. Read and then you decide. Okay. Okay, so then the next step is, if this QPPT is greater than Q target. Okay, remember the Q target is what we say the desired rate, how much I want to produce. Can be plateau, can be any rate. Then produce Q target and move to next time step. Okay, so you have these two options. If QPPT is actually less than Q target, okay, then that means you cannot produce Q target. Okay, then produce QPPT and move to next time step. Okay. Then for the next time step, you simply calculate, for example, here the delta QP will be delta T times QPPT, and here it will be delta QP will be delta T times Q of the plateau or target. Okay. And then you simply repeat. Okay. So if you see, it's let's go to, I think, where is day 24? Already quite a few, more than a week. Okay, here we use like another approach. Okay, here we came and we fixed the rate. Okay, and then we calculated the delta P of the choke. Okay, from counter current and co-current. What I'm saying here is that you had the potential curve only, you have that rate, which is your desired rate. Okay, I want to produce 20 million. And then at this GP, which will be 0, you have another column that says production potential. That will be this straight line. Okay, and then you say, well, at that GP, I could produce, instead of 30, I could produce whatever the curve says here, 52. Therefore, I can produce 20. Okay, and then I move to the next time. And the next time I say again 20, and then I calculate the new GP, which I have to say I have produced, in this case, 20 or 30 during the first year. Okay, and then I find a new maximum rate. Maybe we can do it very quickly. Okay, so let's say time. Okay, in years, 0, 1, GP, sorry, GP, here will be 0, wow, so it's too smart. Okay, then we have the Q target, okay, or Q plateau that I want, which will be 30. Okay, that's what I need. And then you have the QPP, that is again this number. And remember, what equation did we have for the QPP? Do you have it there someplace? This equation, okay, take a copy of that. Okay, so this will be minus 2.09 e to the minus 4 times the GP, okay, plus 51.7 e to the 6. Okay, so that tells me I want to produce this, I can produce much more. Okay, so then I go to the next time step. Next time step, I say I have been producing this number times this guy minus this guy, and multiply times the number of days in the year, which remember to block. Okay, and then again you drag this guy here, you say I can produce 4.3, I need 30, so then I can still keep producing that. Okay, when this one becomes smaller than 30, then I will have to produce QPP. Okay, more or less clear? Yeah. Maybe you can put here Q plateau, so Q desired, but here we have actual Q of the field. Okay, and to make it in a more automated way, we can use an if statement in Excel saying if this guy is greater than this guy, okay, then simply produce this guy. Okay. Or if otherwise, okay, simply produce this guy. Yes? That's what we are saying. If it's greater, then you can produce the target. If not, you have to produce what you can, okay, the maximum. And that is the number that you have to use for the GP. So that's the number that we have to use. It will be the previous. So see, here we forgot to sum the previous plus this rate. Okay, and then I can drag it for all the years I. Oops. Okay, and here I enter already into decline, I think, but I think don't have enough decimal points. Okay, you see here I stopped. Here the potential became less than what I want to produce, so I enter in decline. Okay, exactly the same as we had here. Okay, exactly at the same time, because the potential is following the same curve. Okay. Yeah. Okay. Just put that here. Okay, and that is the equation of the potential. Here we have QPP, and this one X will be actually GP. Okay, that is if of course you have a straight line, you have an analytical expression. Simply you have to make that integration. Okay, what we did before. But if not, let's say you have a shape which is it might happen. Okay, for example, your potential versus QP. Okay, for example, you have is a straight line for some part and then it becomes a curve. Okay, that happens typically when you have, for example, an undersaturated part and then you start having gas coming out of solution. Okay, or if you start having injection. Okay, you have some injection happening. So here you have change of trend due to saturation, for example. Okay, due to injection. Okay, if you have, for example, some gas injection initially and then you change to water injection, it will have a different slope. Okay, or it will have a different shape. Okay, for these cases, then that you don't have an analytical equation, you cannot fit an analytical equation to this QPP, then you might use this procedure. Okay. Okay, so let me just put here the comments so we remember what we're discussing here. Okay, might have a nonlinear behavior and then it becomes a bit more difficult to integrate. Yeah, that clear? Yeah. Okay. Let's go now finally to our topic today, which is networks. Okay. So the Snow White example, we were able to solve it because we said it's symmetrical. All wells are identical, so I can just look at pipeline, flow line, and then well. Okay, simply I have to take care of the rate that is different in each segment. Okay, but networks, usually I have to solve a network. I have to solve the system of equations. Okay, so if I have typically in the North Sea, I have two main development schemes, okay, where wells are typically drilled from the platform, okay, and are deviated. They reach different targets in the formation, okay, that they have to deplete. Okay, and when you have that configuration, it's almost like you had standalone wells. Okay, it's almost like each well you have the separator. Let's make extend the platform here. You have the separator very close to the wellhead. Okay, and then it's almost like standalone wells. Okay, but you have many other cases where you have, for example, an FPSO, okay, a floater. Okay, where you have an FPSO, I have the separator on top of this FPSO. That depends on the water depth. We will see later how that depends, but basically I have here wells that they are not too deviated. They go right, usually they go right above the target. Okay, and then let's take out the deviation of this guy. Okay, and then I have, typically what I have, I commingle production from all of these wells, and I use one common I use one common riser to take production to this separator. Okay, so usually that's common riser. Okay, and this guy I call it FPSO, which stands for floating, production, storage, and offloading. Okay. Okay, this guy needs to have that the tanker comes every once in a while, and it comes and there is some sort of a buoy here. They send production from the platform. They hang it here, the hose or the riser, and then they offload. They charge the tanker. Okay, this one is already storing all production. For that case, for this case, we have what we call a network. Okay, a subsea network. Okay, we call it subsea, not only network, but it's a gathering network. Okay, if you see it from the top, okay, you might have, for example, a few wells, or it might be a few well clusters. Then I have some other wells here. Okay, what we saw in Snowbite, and then finally I get to the separator. And the main thing here of this distribution is that each well depends or is affected by the production of other wells in the network. Okay, therefore I usually, this analysis that we have made from coming upstream and coming downstream and checking the difference, usually I cannot use that because I have to solve everything at the same time. Okay, because they are affected, they are interdependent. Okay, yeah, so just a few definitions here. So typically, either if it's subsea or if it's onshore, okay, I call a cluster of wells, a well cluster. Typically, this piece of pipe that is joining the production of that cluster to a main transportation pipe, taking it to the separator, is what we call the flow line. And this main transportation pipe, that is usually big diameter, that takes to the FPSO or to the platform or to the processing facilities, this is called either a pipeline or is also called a trunk line. Okay, usually onshore we use more trunk line. And in the North Sea, it's and some places in offshore Africa, they like very much these concepts. Okay, you don't need to because the other the alternative is to have a pipe for each this is another color. The alternative is to have a pipe for each well that will go separate to each. They will go separate to the FPSO, and that is the dream of every reservoir engineer, okay, or every production engineer also, to have simply you have your own well and you can see exactly all the values you measure, they are from that well, and you can do a lot of analysis for your particular well. But this is usually too costly. Okay, it is too costly to add separate risers, or in this case pipelines for each well. Okay, simply because of cost. Now, how do we solve this system? So let's see how to solve networks. Okay, and let's look first at one case, and you're going to make now one exercise that was in, I think that was the exam of 2017, I think. So you have, that's how we make a choke. Okay, we have a choke, and then we have a junction. We have well 1. So we have PWF 1. We have PWH1, we have P junction, and we have here, I'm going to struggle to make it properly. So here we have usually the choke is a symbol like that. Okay, you will see in some drawings, and you have a hat here that it tells you if it's adjustable or not. Okay, but the choke usually is like has that that shape, or that diagram. Okay, and then how do we make my other well? So here I have a common P junction, P wellhead 2, PWF2, then I go and I reach the separator. Okay, so let's take that example and let's try to solve it. Let's say it's a dry gas, so let's try to solve it with the equations that we already have. Okay, dry gas network that we use for Snow White. The tubing equation, the flow line equation, and the IPR. Okay, all of them are producing from a PR, which is, let's say, is the same for now. Okay. So let's first make the accounting of, let's say first open choke. Okay. Okay, let's make the accounting of equations and unknowns. Okay, so going from bottom up, we have number of equations, number of unknowns. We have, for example, the IPR equation, right? Q well 1, CR1, PR minus PWF1 to the power of n. Okay, so we have two of those. How many equations? Two equations. And unknowns, we have two rates and two bottom hole pressures, right? So we have 4. Then we have, that's the IPR, the TPR, that was Q well CT PWF squared over e to the s minus PWH 0.5. Okay, so here you have how many new unknowns? I guess only 2, right? But you have 2 more equations. Yes, because the rate we already had it from the previous equation, and PWF we already had it from the previous equation. So the only 2 unknowns we have, one for each well, is PWH. Okay. Next we have the flow line equation, okay, the pipeline equation PPR, which is the Q of the field, is CPL P junction minus P separator squared 0.5. So how many unknowns we have here? New unknowns, we have the rate and PJ, right? And we have one more equation. Yes? So we have total here, we have 8, and here we have 5. We need 3 equations. How do we solve this problem? Okay. One thing you have to take into account for networks, we always have to have mass conservation in junction. Okay, that means that QF, you have, in this case you have just one junction. Okay, so you say that QF will be equal to Q1 plus Q well 2, right? Always, network, always I have to make conservation of mass in junction. Okay, so there I have no new unknowns. Okay, but I have one more equation, and I still need, so here I have 8, I have 6, I need 2 more. What are the 2 more equations? 2 additional equations. The other one is pressure balance in junction, right? If the choke is open and we say this space is very, very close, okay, we can say that PWH1 is equal to P junction and PWH2 is equal to P junction. Okay, if, only if the choke is open and if they are very, very close. Let's make that comment here. Okay, so here I have 2 additional equations and I have no new unknowns, and that the total is okay. Then the total is, I have 8 here and I have 8 here. Yes? Okay, and then it's consistent. That's what I have to solve. If I put that system together, okay, that's what I have to solve. Okay, so for so here I have a system of solve to find rates. Okay, to find rates. Okay, so now I want you to look at, let's take exactly the same system, okay, that we had before. That will be 1, and here I say open choke, so I'm not going to paint the choke, PJ, okay. Then you have this other PJ, PH2, and PWF2, and here I have this other system, okay, with the separator, which is also PJ. Okay. If let's calculate PJ seen from 1. Okay, if I say PJ, I want to plot PJ1 has a function of the rate of 1. I think we have done this before, but for the single well case, so okay, so how does that curve look like? Okay, PJ1 okay, depending on the rate that is circulating through here, Q1. Not 2, but 1. How will that curve look like? If I have 0 rate, I have no production, simply I have a number which is reservoir pressure plus the hydrostatic head, okay, plus the gas column. Okay, what happens when I increase the rate? The pressure will decrease, right? All of you see that? Yeah, because before I had reservoir pressure minus the hydrostatic losses, but I have now, when I increase the rate, I have reservoir pressure minus the hydrostatic minus the friction through that pipe, okay, through this pipe. So this function looks something like that. Okay, and this we call the available pressure at junction seen from well 1. Okay, that's the available pressure that I have seen from well 1. How will it look like for well 2? If I do the same, but now against Q2, exactly the same, right? It's going to look exactly the same for the same reasoning. Okay, and then I have the junction, P of the junction. If I plot it against the Q of the field, okay, that I have here, how will that function look like? Will that curve look like? Decrease. That if it's 0, right, the rate is 0, that should be equal to P separator, right? So here I have P separator. Now what happens if I increase the rate? Now it's not 0, now I make it different than 0. I have to sum not only separator pressure, but I have to overcome all pressure losses in the pipe, okay, all friction losses in the pipe. Therefore, it will be going up, okay, right? Because for this guy, for this point here, I have not only equal to separator pressure, but I have to overcome all of these pressure friction losses along the pipe, okay, and that is exactly this difference that I have here. Okay, this is delta P friction, and it actually is increasing like that. Okay, so you have, just to wake you up, we have an exercise. This was in the exam 2017. Okay, so you have exactly those curves, and you have to find out how much I'm going to produce. If I put all of these pieces together, okay, these three, how much will the system produce? That's the first question. So how will you go about it? How will you Um, any ideas?
You have to find an optimum rate.
No, you have to find a way. Simply, I say, I have two wells in a field. Okay, can be offshore field, can be onshore field, and I want to tie them with a pipeline. I want to see how much the system will produce and how much each well will produce. Okay? That's a typical task. They tell production reservoir engineer, calculate if I put the system together, how much it will produce. Okay? I'm going to give you some time. Yeah, we'll give you like, let's say 10 minutes. Will that be okay? So just keep in mind, the pressure at this point seen from the choke is fully open, right? So the pressure seen from here, from here, from here should be the same. So I have to make sure that pressure is the same. Okay? If I come with this rate, let's say I assume this is the rate that will be, okay? And this is the rate that the well will produce. Okay? Is that pressure equal to that pressure? If not, that means that's not the solution. Okay? Because any Q that I guess has to have the Q that I guess for this one and the Q that I guess for this one should be the same PJ, should have the same junction pressure. Okay? And moreover, then the rate that I assume here and here, when I put it here, it should give me the same PJ. Right? Because all the pressure seen from different sides, this is that point, the junction, seen from the separator. This is the junction seen from well 2, and that is the junction seen from well 1. So if I guess these two Qs, they have to have the same PJ, and when substituted here, the sum has to have the same PJ. If not, I repeat. Okay? So I give you 10 minutes, and then we discuss in plenum. It's not so, this example only with two wells is not so trivial, okay? And in reality, when you're using a simulator, that part will be taken care by something like this, okay? But I think it's important that you see the kind of the complexities of that you have when solving even such a simple problem, okay? So you can do what I told you before. For example, you can guess Q1 and Q2, okay? So one possible option is to guess Q1, okay? In our case, let's say, I don't know, 1, okay? And that gives me a pressure of 76, is it? 1 e to the 06. The PJ seen from 1 is 76. Then Q2, let's say I guess 1 maybe. Okay, and I'm here, and that is how much? Like 90. Okay, so I know already I kind of messed up. And then I go to Q of the field with 2, okay? It will be the sum of the other two, of 1 and 2. So PJ here with 2 is actually, how much is that? 54, okay? Okay, and all of them should be the same. The PJ seen because the choke is fully open. So that's not the solution. Okay, I have to iterate once more. However, in this case, iterating with both P1 and 2 is like very complex. Okay, what do I decide now? Should I increase Q1 or should I decrease Q2? Okay, from what I have here, I could say, well, I should increase Q1. Okay, such that the pressure that I have is not 70, but it will be a bit lower. Okay, because I know this pressure has to go down to 54. And also I should decrease Q2, increase Q2, okay? Because the pressure should be below 90, should be someplace here. Okay? But like Arpita already discovered, and I think some of you, that is much better to iterate with Pj, okay, with P junction, because you have one variable which is common for all of them. Okay, you don't have to be iterating with Q1 and Q2 because can get messy. You exactly how to change them, how much to vary them. So if you integrate simply with Pj, okay, and let's say Pj equal, I don't know, let's try with 50, okay, then you read Q1, okay, Pj 50 from 1 is how much? 1.2. Q2 it's 50, okay, 1.5, how much is that? That's 1.6, 1.57 maybe. Okay. And then you read the Q of the field, that will be with 50 here, so you have 1.5, 6, 7, 8, 1.8 e to the 6. Okay, and what do we do next? We simply sum up, right? These two guys should be equal to this guy. Okay, so we simply make a sum, and at the end we end up with, this is 2.77 minus 1.8, that is around 1. Okay, so we have 1 million which is in deficit. Okay, we are producing two, according to what I should be producing, I'm producing too much. Okay, so what should I do? I should produce less from the wells, okay, and I should produce more from the network, okay, to bring them close. So I have, the conclusion is to produce less from the wells. I have to increase pressure, right, from 50, and I have to increase pressure. That will give me higher Q, smaller Q2, smaller Q1, but bigger Q of the pipe. Okay. Then I try PJ. Let's say I don't know. It could be, let's try a high number, 70, for example. Q1 with 70. Okay, it's like 1 point. This is 1 point. How much is that? 1.06. Okay. Q2 for 70 will be someplace here. And how much is that? 1.35. Yeah, more or less. Then I go here with 70, and so I have 3, 2, again here I think is 2.8. Okay, the sum, that will be minus, right? Minus 0.5 1 3 39. Yeah, 6, that will be give you 41. Yeah, 39. Okay, so you can, if you try a bit more now, you see you're getting closer, and that's actually quite close. Okay, so if you maybe can try, you know, that this chord method, okay, you have some error function that will be q of the field minus q1 minus q2, okay, versus pj. We have one number that we tried, pj was 50, okay, which is here 50, and we end up with 1 e to the 6, and we tried now 70, and we have 0.39. okay, you can make a straight line, okay, and then you can find out for what pj will be 0. Okay, we say 1 e to the 6 minus 0.39 e to the 6 over, it should be minus minus, right? So it should be here okay. And here we had 50 minus 70, and here I will have between any 2 points, okay, for example, let's use 1 e to the minus 6, okay, minus 0, okay, I want that y to be 0 exactly, divided by 50 minus the pj, which is the solution. Okay, and from there I clear, simply making the slope is the same. Okay, I'm making the slope from here to here should be the same that from here to that point, the intersection. Okay, and then I find out from there, I clear how much is my x. And some people have done like that in the exam. Some people just tried, you know, any number now between 50 and 70. Okay, they start to try more and more. Okay, but that's a way that I can approximate with a straight line the error function, and from there I find how much is the intersection. Okay, that clear? I don't want to break for a break, so let's take now one last thing, and then we finish you know, the lecture. The other question in this exam was that if I now want to produce Q1 1.9 and Q2 0.8, okay, and the question was, is this possible? Are these rates possible? Hmm? 1.9 from Q1.
It should be otherwise.
Sorry, yeah, you're correct. Q1 let's use, I think maybe that's let's use let's say we want to produce less, okay, instead of 0.8 and 0.8. okay, is that possible to produce those rates? Well, first you want to see if they are below the no choke, right? Because I see the no choke solution. How much was it? I think some of you found it. The solution is, I think PJ, I think it's 64 64 bar, 1.1 and 1.45. Okay, that's the solution. 64 bar and Q1 is 1.1 and Q2 is 1.45, I think. Okay, so first you have to check that the rates that you are producing, okay, 0.8 and 0.8, they're actually below these two. Okay, that's almost a good indication. You say, well, I think they should be able to produce, but then my system, I cannot put them together simply like that. Okay, I have to use a control element, which is missing now, will be the choke. Okay, that's the only thing I can use to control this system. It's a dry gas system, I don't have any pumps, I don't have anything, so I have, at the wellhead, I have to use the choke to control and get exactly 0.8. Okay, so let's go again to our plots, okay, and let's do exactly what we have done for the Snow White case. So I impose the rate, okay, for example Q1 0.8 and Q2, right? That's what we have done for Snow White. We impose the rate. We say we want to produce 20. Okay? Then we go and calculate available pressure and required pressure at junction. Right? We took one equilibrium point, which was the choke. We know our choke will be between the wellhead and the junction, someplace, right? But we said at that point I will calculate the pressure required and the pressure available. Okay, and in this case I have two pressure availables and one pressure required. Okay, so what is PJ seen from 1? If I use 0.8. Okay, 0.8, it's here, right? That will be 96. Yeah. PJ1 is 96. PJ2 is 100. And PJ from the separator is how much? So it will be 1.6, right? Which is here, and 40, yeah, like 45. You see that there is an imbalance of pressure. Okay, I have much more pressure in these two guys than what I need. I need 45, but I can then breach. If I say I don't go now to the junction, okay, I calculated the pressure up to here and the pressure also up to here. Now if I put an element in between to break that pressure down, to bring that pressure down, okay, to the junction pressure, so I have my delta P choke 2 and delta P choke 1, then it might work. Okay, I am breaching the pressure, so the delta P choke 1 will be from 96 minus 45, okay, from what I need, and the delta P choke 2 will be 100 minus 45 bar. Okay, so how much is that? That is 55, and this guy is 51, right? Okay, that means that if I want to get 0.8 and 0.8, I should add a choke between. Now it won't be P junction. Okay, now this PJ won't be P junction. This will be P wellhead 1, and this will be P wellhead 2, because now the choke is not fully open anymore. Now it's closed, and now that makes a difference between this point and that point. They are not the same. Okay. Now, can I get any combination of rate, you think? If I say now 0.5 and 0.4 and 0.1 and 0.3, can I get any combination?
Yes, if we use choke, we can.
Yes, okay, but there is a but. So let's make a plot very quickly. Okay, we have the Q rate 1 and Q rate 2 of that system. Okay. When is fully open choke, okay, we have a point here that we found is 1.1 and 1.45. Okay. Now, if I start to choke only one of them, okay, let's say I operate only with well 1, do you think that it will produce more than 1.1 or less? Operating only with well 1. Okay, well 2 is 0, right? And well 1 usually can produce a bit more because it's not competing anymore in the pipe with well 2. Okay, so that will be with well 2 closed. Okay, shut in. And at this point, if I shut in, let me bring it down. Okay, if I shut in well 1, okay, that will be at 0, then I can produce a bit more than 145. Okay, this point will be with well 1 closed, shut in. Okay, and then you can say that if I start choking, here is fully open, and if I start choking only well 2, okay, I have start closing well 2, closing well 2, it will follow more or less that line until I find here, okay, until I find fully only well 1 circulating through the network, okay. Or if I do the opposite, I start to close well 1, close the choke of well 1, close, 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 it will get to this point, okay, where well 1 is fully closed, okay. And you see now a region that comes up. Okay, so this will be closing choke 2, okay, choke 1 fully open, and this will be closing choke 1, choke 2 fully open. Okay, so every combination of points that I have inside this area, inside this, it will be feasible. Okay, I can find any choke opening, 50% or 30-20%, or to produce these rates inside. Okay, but everything outside will be unfeasible. Okay. Okay, so if a reservoir engineer says, I want to produce so much from one well and so much from another well, the production engineer will come and check, are they inside? Is it something that I can reach? Or maybe something that I cannot reach, okay? What happened in the simulator, if you try a combination that is here, you will never find a solution. Never. It will never converge, because simply these rates are not feasible. But if you try a combination which is here, then it's just a matter of finding the choke. Okay? That clear? More or less? Yeah. Okay, what happens with time on this chart? With that area, with that feasible region?
It will
Shrink. Okay? Because reservoir pressure, let's say the maximum rate you can produce when well 2 is choked, okay, will be reduced with reservoir pressure. Okay? That rate will also be reduced with reservoir pressure, and therefore this one with open choke would also be reduced. So when reservoir pressure is reducing, you are getting less and less range of operation, okay, or of my network. Okay, so let's put that comment here, PR1, and then you are PR2. Okay, simply H rings. Okay, before we close, any question? No? Okay, have a nice week and see you on Friday.